All right. So does anyone have any? Oh, this is the third hour of Physics 1A for March 29th, and just gonna start by saying, does anyone have any questions about what we just discussed? $180 for the force of gravity right here. So for work, what you do is you take the direction of the force, which in this case is down, and the direction of the displacement, which is up. And we basically want to find the angle between those two vectors. So if I put the two vectors like side to side like this, it should be pretty clear that the angle between those two vectors is 180 degrees. It's the full 180 degrees. Does that answer your question? Oh, okay. All right. So what about this conservative force thing? So we said that work done is independent of the path taken. We define the work done by gravity, the potential energy due to gravity to be this, the potential energy due to the spring force to be this. And it allows us to basically calculate work without having to use the equations from before. You just need to know what the potential energy function is, and you can use it to find the work done by these forces, which is going to become very handy for solving problems that involve changes in elevation, as well as springs, as well as kinetic energy as well. All right, so we talked about a conservative force, and I said that it's independent of the path. So let's briefly talk about non-conservative forces, and let's put all this stuff together. I'm just going to use an example to describe what these are, and then I'll give you a list of other forces. So the simplest example of a non-conservative force is friction. So what we'll do is we'll basically say, suppose that I have a tabletop that we're looking down on. So this is a table, and we're looking down on it. So the ground is into the screen, and things are on this table. On this table, let's say that I have a box, and I'm going to move my box between 3 points. We're going to say it starts off at point 1 right here, and it's going to move to a point over here that I'm going to call 3. But we're going to do so along 2 different paths. One path is going to take the block from point 1 to point 2 all the way to point 3. So one path is basically going to be like this. We're going to go this way, and then we're going to go this way. Those are going to be the 2 displacements that we travel along. And then the other path that we're going to take is going to point at an angle, and it's going to be basically like this. So pretty consistent with what we did with, we'll call this path 1, 3, and then we'll call this path 1, 2 down here, and we'll call this path up here 2, 3. All right, so when we move the block from 1 to 2 and then 2 to 3, and then we take the block and put it back to its original position, we move it from 1 to 3, which path requires, or along which path does friction do more work? this one. And it's purely because the force of friction and the work done by friction really has everything to do with how far you go. Okay? So if we assume the friction is the same in both cases, then it's really just about in which case did you go farther. Okay, so this is what makes friction a non-conservative force, because the work done does not just depend on the endpoints. In both cases, we have exactly the same endpoints, but the work done is going to be different. Does that make sense? So a non-conservative force is one for which work done depends on path. And I can say pretty much any force in this course that is not gravity and is not a spring is going to be a non-conservative force, okay? So examples of this is everything else. That would be the drag force, obviously friction that we just talked about, tension, the force of an engine, like a car, the force of pulling or pushing by a person. Every single other force that there is going to be a non-conservative force. Okay, this is kind of like, you could think of this as all other forces than gravity or springs. And also the electric force, and also some other things that you'll learn about later. But for this class, this is all that you need to know. Is that all of these things are non-conservative, right? Okay, so this is how we tie all these concepts together. So the concepts we want to tie together are kinetic energy, potential energy, and work. We want to basically tie all of these into one equation, all right? Now, the first thing I'm going to point out is that kinetic energy and potential energy together we call mechanical energy. So sometimes you'll see this type of thing written down, that E is equal to K plus U. When this is written, I really don't like this equation very much, but you will see this show up in your textbook, so just so you know what it means. I think a better way to write it would be mechanical energy is equal to K plus U, but regardless, this sum, the kinetic energy of a system plus the potential energy of the system, we call this mechanical energy. That is to be kind of distinguished between things like thermal energy, which is the energy that is sometimes referred to as heat or temperature, electrical energy, which would be the energy stored, let's say, in a battery, chemical energy, which would be the energy stored in food, and radiant energy or light energy that comes from the sun. Mechanical energy specifically is kinetic energy and potential energy. All right, so this is how we're going to tie all this stuff together. So we had the work energy theorem from before. Which said that the work done by, the example we used was a car, was equal to the change in kinetic energy of that system. So the next thing we want to do then is we want to distinguish that there are two different types of work. You're going to have the work done by non-conservative forces, so the work done by NC, plus the work done by conservative forces. Okay? And that should be equal to the change in kinetic energy of your system. But when we talk about a conservative force, there is something that we can do with this here. We can say that the work done by a conservative force, if we go back and look at our two examples, the work done by gravity and the work done by springs were both conservative forces, and in both cases, the work done was equal to the negative of the change in potential energy. Right? So we can replace the work done by a conservative force. We can't replace this one. Oops. So we can't replace work done by non-conservative forces. We leave that one there. But for the work done by conservative forces, we're just going to use this relationship. The work done by any conservative force is always equal to the negative of the change in potential energy for that force. So we replace work done by conservative forces here with the negative of the change in potential energy. And then we're going to add this piece to the right-hand side. And we're going to get the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And in this equation, it's probably one of the most useful in all of physics. There's another way you could write it using mechanical energy. So another way you may see this written is the work done by non-conservative forces is equal to the change in mechanical energy. I'm probably not ever going to write it like this because I think this is very, very confusing. But if you want to write it like this, it's fine. I will understand what you're writing. This is like the kind of thing that I might do if I was working things out myself. But in general, I will always write it like this. So this is a type of... It's not exactly conservation of energy, but that's what I'm going to refer to it as. And basically what this statement says is that all the stuff on the right side would be 0. That is to say, the total of the change in kinetic plus the change in potential energy of a system would be 0, unless you have non-conservative forces acting. When you have non-conservative forces acting, they're going to have the effect of changing the total energy of your system. That's what this equation basically says. So I'm going to call this conservation of energy. When I say, like, how are we going to solve a problem, and I say, okay, we're going to use energy conservation, this is what I mean. I mean that we're going to use this relationship right here that tells us that if I have any non-conservative forces, I need to include them. If I don't, the left-hand side will be 0. So if your problem doesn't have any of these things, then the side will be 0, and then you'll just get change in kinetic energy plus change in potential energy equals 0. But anyway, that is our relationship that we're going to use to solve all the problems we're going to do for the rest of the class today. Very, very powerful equation. It relates work done on a system to the change in energy. Does anyone have any questions? So, everything we've done today is very theoretical, right? Let's go back through what we've done. We're now going to do some problems. I just want you to kind of like understand that up till now, all the stuff we've done is very theoretical. So we defined what work was, right? A force applied over a distance. We used this equation to talk about constant force. You take the dot product between force and displacement. So now we know what work is, right? But that wasn't enough. We also had to include the work done by a force that varies in some way. Looks like this just isn't loading right now for some reason. Okay, there we go. That wasn't enough. We had to also include the work done by a variable force. And we needed that because we wanted to include springs, because it turns out that the spring force is a conservative force. So we had to introduce that idea. And then we had to develop the concept of kinetic energy, where we basically found out that kinetic energy is just 1/2 mass times velocity squared. That's all that you need to know about kinetic energy. And then we said, oh, well, kinetic energy and work are actually connected to each other. The work done on a system has the effect of changing the kinetic energy of the system. And then we said, okay, well, there's another type of energy we can talk about, which is called potential energy. It's stored. It can be stored in the form of gravity or a bowstring. And that same type of potential energy gets applied to springs. And we got these two relationships. Potential energy of gravity is mgy. Potential energy of spring is 1/2 kx squared. And once we have that, and we introduce the concept of non-conservative forces, we finally get this one equation right here. Now, this equation is extremely powerful, but not if you don't know what it says, right? So, just as an example, if I want to expand out what this equation actually states, really what it says is, on the left-hand side, you have to sum up all the work done by various forces. So this could be the work done by friction, the work done by whatever. So in general, we just say all of that together is the work done. I swear to God, I picked black, but it didn't switch. I don't understand. Why is it not switching? This is so frustrating. Whatever. We'll just keep going in the same color. All right, so this is what this equation says. It says work done by non-conservative forces is change in kinetic energy. Well, what is that? That's going to be 1/2 the mass of this. You'll have to write this down for every thing in your system that's moving, because it'll be a whole system, 1/2 the mass of whatever object multiplied by v final squared minus v initial squared. That's what the kinetic energy change is going to look like, plus the change of potential energy. So you could, in principle, have an object that changes its elevation. So that would be the change in gravitational potential energy. You could also have an object that that you could have a spring in your system. So you could also write 1/2 k times x final minus x initial, remembering that these terms represent the compression of the spring. And that's basically what the equation states, at least for what we've learned up till now. There will be other terms on this equation, as we learn about another form of kinetic energy called rotational energy. That'll show up in this equation. And then when you take things like physics 1c, you'll notice that there are other things that show up in this equation too, such as the electric potential energy. But that's basically the equation that we're going to use to solve not problems just in this chapter, but problems for the rest of the semester. This is just a really, really, really powerful and valuable equation here. So I've got a few problems I want to work on to solve these. We'll probably have to just go to another slide because I can tell that OneNote is just pushing the limits of how much memory it can use or something like that. I don't know what causes this. So let's grab, we'll just do one at a time. This is the first one we're going to do. And I think we'll have time probably to do 2. And if we're going to do 2, I guess I'd like to do these 2. That probably makes the most sense. All right, so let's do that. Let me interact with this in a way that isn't crappy. Click. This is great, because when I click the bottom one, it's not moving. Alright, there we go. Alright, so this is the problem that we want to solve. Alright, so we have a 4 kilogram block. This is the block right here. And it's attached to a spring. It says it compresses the spring with a spring constant of 24 newtons per meter by 1/2 meter. So this is the equilibrium position of the spring right here. And the box has basically been pushed to this position here. So the box is starting right here, 0.5 meters to the left. And it says it's then released while at rest. We want to find the velocity of the block when the spring is compressed by 0.3 meters, if the surface is frictionless, and then if the coefficient of friction is 0.1, and then we'll figure out how far the box slides. Okay, so this block is not physically attached to the spring. It's free to basically be released from the spring. So the block is basically just put up next to the spring, and then we compress the spring by 1/2 meter, and we want to calculate what is the velocity when the spring gets to this position here. So this is going to be our x initial, and this is going to be our x final. And the question is, how fast is that block moving when it gets there? Right? Yeah. We want to calculate what the velocity at this location is. I'm going to call that v final. And I think this picture is kind of hard to actually view, so I'm going to draw my own version of this, but so we're going to have kind of an initial position like here. And we're really going to need like 3 different positions, but I guess for the first part we just need 2. So we start off with our block here, and the block is going to move to like here. Maybe like here, so we have enough room. And in both cases, we've got a spring connected to the block. It's a little bit compressed right here. I'll just put a little like something like that to indicate that they're not attached to each other. And then this one is slightly less stretched. Here. Again, the block is not actually attached to the spring. And we're saying that this position here is going to be x initial. This is going to be x final. And these positions are going to be measured relative to the 0 point, which I'm going to say is right here. So this is x equal to 0. This is the positive x direction. And it says that the block, so it says, let's read it again. 4 kilogram block, so it has a mass m. The mass is 4 kilograms. We have a spring constant. The spring constant is 24 newtons per meter. And instead of writing them on here, I'm just going to say we'll have an x initial and we'll have an x final, at least for the first part. And maybe I will write them on here. What are those going to be equal to? What would x initial be equal to? If this is x equal to 0, x is positive, and it says that it starts at 0.5 meters, what is x initial equal to? That's right, Andrew. What you said is right. Your clarification there. What would x, negative 0.5, exactly. So x initial is going to be negative 0.5 meters. It says we want to find the velocity when the spring is compressed by 0.3 meters. So that means that's going to be our final position here. So this is going to be also negative, right? Negative 0.3 meters. Now, we're going to need to throw some velocities in here too. What's the initial velocity of this object going to be? Yep, 0. And what's the final velocity going to be? We don't know. We're trying to calculate that, right? God, why does it always have to do that? Equals question mark. There we go. All right. That's our scenario, basically. You start off with the block here. It's released from rest. We want to find the speed here. And we're going to do in part A, we will say the first surface is frictionless. So let's do part A first. All right, so we're going to start off with our equation, which is work done by non-conservative forces is equal to change in kinetic energy of the object plus the change in potential energy of the object. So since friction is 0 and there are no other non-conservative forces in this problem, the left-hand side of this equation will be 0. So we're going to have 0 is equal to change in kinetic energy is 1/2 mass times V final squared minus V initial squared plus, for change in potential energy, there's technically two different types of potential energy we in principle could have. There's the potential energy due to gravity and the potential energy due to a spring. Because this object is moving along a level surface, what is the change in potential energy? And it's the change we care about, not the absolute value. What is the change in potential energy due to gravity going to be if we move along a level surface? 0, right? So we just need to add the change of potential energy to the spring. So we write down what that was. It was 1/2 times k multiplied by x final squared minus x initial squared. And I'm just going to keep reiterating this every time I write this down. The x here, all that it represents is how compressed the spring is. That's it. If there's no spring in the problem, this is always 0. Okay, the next thing we're going to do is we're going to look at what we know. So we know that V naught is 0, so we'll just do that. We're looking for V final, so let's move the V final to the left-hand side of the equation, and then let's solve. So we're going to have 1/2 mv final here, so when I move it to the left-hand side, it's going to become negative 1/2 mass final velocity squared is equal to 1/2 of k times x final squared minus x initial squared. And we just want to solve for v. So isolating the velocity, we're going to get final velocity is going to be equal to the square root. We need to divide by m, so we're going to have k divided by m multiplied by x final squared minus x initial squared, and I've canceled out the halves. Because there's a half in both sides, we could just cancel those out. So that becomes our expression right there. I don't think there's enough room to write this over here, so we'll scroll down just a little bit. I don't want to go too far because we want the problem still to be here. Okay. So plugging in the numbers that we have here then, we're going to have V final is equal to the square root of k. K was 24 newtons per meter. Oh yeah, this is negative. Because of that negative sign right there. You're right. So we'll have negative 24 divided by the mass, which is 4, times x final was negative 0.3 squared minus x initial. Close parenthesis, and then move the radical all the way to there. And perhaps you all can calculate this. Let's see. So this is going to be 0.4 squared, which is 0.16. 24 over 4 is 6. 6 times 16 is 256. But it's going to be 2.56. No. It's going to be 0.256. What's the square root of 256? I don't know. It's going to be something like 0.5. No. That's probably wrong. What do you all get? Oh, 6 times 16 is 96. So actually, the answer is going to be like 1. It's going to be like 0.9 something. Yeah, 0.98. Yeah, 0.98 is fine. We'll just write it like that. Okay, this is with no friction though, right? That was the part A part. Okay, so let's do part B. We'll use a different color. It says if the coefficient of friction is 0.1. Okay, so we can basically do everything that we just did, except we need to change this piece. The work done by non-conservative forces is no longer going to be 0, right? So let's see how much of that we can squeeze in over here. So once again, we start with our equation, which is going to be work done by non-conservative forces is going to be equal to change in kinetic energy plus the change in potential energy. Now the work done by non-conservative forces is going to be the work done by the force of friction. And to find the work done by friction, we basically, what we want to do is we want the force of friction multiplied by the displacement, delta x. But really, we just want the absolute value of the displacement. And there's going to be a negative sign that shows up here. And in order to make sure that that's not super confusing, the negative sign comes because the friction force is going to be acting to the left, and the displacement is to the right. So that's delta x, and that's the friction. They're 180 degrees away from each other. So the left-hand side of our equation is going to be friction force times delta x times cosine 180. And we're saying the coefficient of friction is going to be 0.1. So all of this will be equal to the right-hand side. The initial velocity is still 0. Let me scooch this over to the left so we have some room to write. So we have, on the right-hand side, 1/2 mvf squared plus 1/2 k. Okay. For the left-hand side of this equation, the friction force is going to be basically, the cosine 180 is going to give us a negative sign. The friction force is going to be mu k multiplied by the normal force. Because it's a flat surface and there's no forces pulling up or down on the box, this is one of the rare cases when the normal force is going to be equal to mg. we need to multiply that times delta x. Delta x is basically equal to, well, I'll just leave it as delta x. I'm going to keep putting these bars around here to indicate that we do not care about what the sign of delta x is. And all of that's equal to all this. If you have any questions at all, please feel free to ask. Now we just need to isolate v final. So we'll add this term to the right-hand side. Or maybe, it doesn't really matter what we do. So we're going to have negative 1/2. We'll add this term to the right-hand side, so we'll have mu k and now we just need to kind of do one more final step and then rearrange and plug in numbers. So we're going to end up getting v final is equal to negative 2/m times all of this stuff. I think I'll just multiply the 2/m through everything, because the first term, what we're going to get, I'll make it clear what I'm doing here. I'm multiplying both sides by negative 2/m. So the first term is going to end up being 2 mu k g and it'll be negative. And then the second term will also be negative, and it'll be, the 2's will cancel, but the k over m will stay. And we need to take the square root of all of that. And even though both of these are negative, this term is positive because x final is smaller than x initial. Okay, let me just scroll back up a second and maybe zoom out a little bit. Does anyone have any questions about what we just did? It's really just a bunch of algebra, honestly. And if you hate algebra, you can always plug numbers in earlier if you want to. Okay, no questions at all? Are you all just completely exhausted from 2.5 hours of physics to where your brains aren't even working anymore? Because that's where I would probably be. Oh, we could put a plus or minus sign. Yeah. It's definitely going to be positive, though. So I'm not really worried about it in this case, but you're right. We can put a plus or minus in front of there if we want to. All right, so our answer is going to be plus or minus the square root of, let's plug everything in. We have 2, mu k is 0.1. I'm going to zoom in a little bit so it's a little easier to see in case you're on a smaller screen. All right, so mu k was 0.1. There is a negative sign here, so 0.1, and then g, obviously 9.8. Delta x, okay, so delta x, I'll just write the equation up here. Delta x is basically equal to x final minus x initial. So for us, x final was negative 0.3 meters minus x initial, which was negative 0.5 meters. Look at all these negative signs. But then negative makes it positive. I think you get delta x is equal to 0.2 meters. So 2 times mu k times g times delta x. So that's what we plug in our 0.2. And even if this had given us a negative number, I would still have made it positive. We don't really care. Really what we're calculating here is the absolute value of this quantity. All right, so, okay, negative, okay, minus k over m. So k was 24. And then m was 4 kilograms. And then all of that gets multiplied by that same thing that's right there. I'm going to drop these negatives. Well, maybe I shouldn't do that. Negative 0.3 meters squared minus 0. Nope. Minus negative 0.5 meters squared. Kind of running out of room here. Close parenthesis. And then we're just going to check, because there's so many things we plugged in there that it's very easy we could have made a mistake. All right, so let's go back to here. So this one had a negative sign on it. We added this to the right-hand side. Everything was positive, but then we multiplied through everything by negative 2 over m because we had to move this one to the left. So the first term became negative 2 this. So there's the 2, 0.1, 9.8, 0.2. And then negative 2 over m times this, the 2's cancel, so you get a negative sign and you divide by m. So you have k over m and then this stuff here. Okay, there we go. So our final velocity ends up being equal to plus whatever you get out of that. I think that's the right answer, 0.75. I'm just going to put that down because I would like to do the other problem too, and we're very rapidly running short on time. Luckily, the other problem is kind of fast. Is it reasonable that the answer is less than the answer we got in the first part? Yeah, because there's friction now, so it shouldn't move as fast. Okay. So this is the velocity the object would get with the spring alone. This is the velocity that it would have if we also include friction. And we're not done. The last part says, part C says, if the coefficient of friction is 0.1, how far will the block slide? I have to decide very quickly here if I want to do this or if I want to do the other problem. I think we're going to do the other problem. To do that part right there, all we really need to do is to say that this spring is going to decompress up to about this point right here, at which point the block will have some kinetic energy, and then the kinetic energy of the block will carry it to the right until it stops. So what will end up happening then is basically that for our initial position, we're still going to say x initial is equal to 0.5 meters, negative. We say x final is equal to basically 0. We're going to assume that it basically decompresses the spring completely. Our initial velocity is 0. We want to see how far it will slide, which means it will eventually come to rest, which means our final velocity is 0. So what we end up doing is work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. The change in kinetic energy is 0. That means the work done by non-conservative forces has to be, it's going to be friction. It's going to be friction force multiplied by the distance traveled. And all of this is going to be equal to the change in potential energy, which is going to be 1/2 k times x final squared minus x initial squared. I said I wasn't going to do this. This part's actually pretty short. I'm doing it faster than I normally would, though. So if you're getting lost, like, I understand. Left-hand side is going to be mu k mg d equals negative 1/2, because x final is 0, k times x initial squared. So the distance traveled ends up being equal to k times x initial squared divided by 2 mu k mg. So this is the answer to part C. And again, I'm just gonna move on. And if you don't understand that, I'm gonna stick right after class. I'll go back and explain to you what I just did. All right, now we're gonna do this one. We've got a little bit of time. If I can't solve this problem in the time we have left, that's fine. We'll just we'll finish it next time. But I'd like to give you at least a couple examples. This is the only example we've done because we had to spend so much time developing the theory. This is part of the reason why the topic we're discussing this week is 2 chapters in your book. It's because there's a lot of theory. And then once you have the theory, you can solve all sorts of problems. Okay, so here's the next problem we want to do. So a block of mass m is at rest a height h above a spring with a force constant k. We want to find the maximum distance d that the spring is compressed. Now, we can do this entirely in symbols, but whatever, we'll just do it in symbols. It'll actually take less time. So that's the scenario. Block starts up here. It's dropped onto some kind of platform that can support its weight. The block hits the platform, which then causes the spring to compress. And at some point, the block is going to turn around and start going back upwards. And what we're interested in is the point at which the block reaches its maximum compression. Okay? That's what we want to do. Now, let's talk in general about how you approach these problems. So, what you may have noticed that we did in the last problem was I picked the two positions, the starting point and the ending point, and I basically went through and I labeled all the variables that I care about, okay? What are the variables that we care about? Well, if we think back to the equation that we used, the only variables that show up are the displacement of the spring, or the compression of the spring, the velocity of the object, and the elevation of the object. These are the three variables that we care about in this problem. Compression of the spring is x, v is velocity, y is elevation above the earth, okay? Those are the only three variables that we care about. So what we really want to show on our picture is what the values of those variables are at two different locations. You need at least two different points to use the energy equation. So we have them. We're going to have the starting point where the block starts up here from rest, and the ending point where the block maximally compresses the spring. And we're basically going to write down what these variables are at each one of those locations. So I'm just going to write at the top right here, I'm going to write x initial, I'm going to write y initial, and I'm going to write v initial, and we're just going to fill that out. I think it's really helpful to have a guide of like what you want to put in. And then down here, I'm going to write x final, y final, and v final. And we're just going to fill out this table here as we do this problem. So let's start off with the easy stuff. What's the initial velocity of the block? What's the final velocity of the block? Yep. If it maximally compresses, if it goes to maximum compression, that's going to be the point when the block turns around. So you're all saying 0 quite correctly. Okay, great. 0 and 0. That's awesome. We don't even have to worry about kinetic energy now, right? Let's go to the next thing, the next simplest. Let's look at the elevation. Now, in order to use the y, we need a reference point that's going to be 0. So we could make the top 0. We could make the uncompressed distance of the spring 0. We could make the bottom 0. It really doesn't make a difference which one we choose, but we can always choose either y initial or y final to be 0. So we might as well do that, right? It'll simplify our calculation. What do we want to use? You want to use the bottom to be 0? Or you want to use the top to be 0? Probably the bottom makes the most sense, because then we have positive y goes upwards, right? Okay, I'm going to say something that it may or may not be wrong. In my experience, when you're doing these type of problems, you basically always want to make up to be positive for y. I think you have to do this. I could be completely wrong. I could totally be wrong about this, but I'm pretty sure you have to do this in these type of problems, or else you have to redefine what potential energy is, okay? So just from now on, just always make y positive up, which that's kind of the natural thing you would do anyway, right? But just be sure that you do it. Okay, so if y final we define to be 0, we're basically just fixing this point to be y equal to 0, this lower elevation here. What would y initial be in terms of the variables given in the problem?
D plus h?
D plus h, that's right. So y initial is then going to be this distance d plus h. Okay, the other two things we need to figure out are the compression of the spring. Now remember, x, it does not represent like just displacement, position, or distance. In this specific context, when we're talking about energy problems, the x means the compression of the spring. So, how much is the spring compressed in the final position? How much is the spring compressed? And this is relative to the equilibrium point of the spring, which is here. This is x equal to 0. So how much is the spring compressed? Like negative d. That's right. Negative d would be a good choice. Really, we could just use d if we want to, though. So we're just going to use d. Because really the question is, how much is it compressed? Because at the end of the day, we're going to be using this equation, right? 1/2 kx squared. So we don't really care if d is positive or negative. That isn't really important for us. But you're absolutely right, Kelvin, in terms of like, if we're going to be consistent, we would put a negative d right here. All right. This is the part that's kind of tricky. What's the initial compression of the spring? It's 0. That's right. Why is it 0? This block isn't even touching the spring. The spring isn't doing anything in the initial scenario. It's not... The block isn't compressed against it. The spring is just sitting there, unstretched, right? This is really, really, really important. And it's something that 10 years ago I didn't understand this, but now I do. This is one of the most confusing things for students, is understanding that this symbol X, while in the past we've used it to represent like how far something moves, the position of an object, things like that, when we're talking specifically about energy problems, it only represents the compression of the spring. So if the spring isn't compressed, then X is 0. Okay, it doesn't matter that the block is really high above here. Okay, so hopefully you all remember that. I'm sure many people will forget. I'll keep repeating it. This is just the compression of the spring. There we go. Look, so many things are 0, right? That means that when we write down our equation, this problem is going to be very, very quick. Okay, so let's start off by writing our equation. Our equation, the first step is work done by non-conservative forces is equal to delta K plus delta U. That's our energy conservation, work energy equation, whatever you want to call it. Are there any non-conservative forces acting in this problem? Nope. That's 0. Almost always, this is going to be something like friction, or if there's an external force pushing the system, that's what's going to show up there. Okay, so we have 0 equals. Now, I know that it may be tedious to write all these out, but I'm going to write them out every single time because I don't see why not. I think it helps to always start from the same place all the time so that you don't get confused as to... well, you just don't want to skip steps, basically, in physics. Especially physics. Like, it's okay to skip steps in physics once you're really, really good at this stuff, but when you start doing that... Look, I don't consider myself to be really good at physics. I just consider myself to be pretty average. I've definitely met people in my life that are way better at this stuff than I am. But the thing that I think allows me to be able to do physics problems and make less mistakes, I would say, than average, is I don't skip any steps, including writing this equation every single time and writing the whole equation every single time. It's just a good habit to get into. It may take you an extra 30 seconds to write the whole equation down, but it might save you 30 minutes later down the line. You know what I mean? If you have to take an extra minute to write a full equation down, but it causes you to not drop a minus sign that you end up spending 30 minutes looking for, then it's well worth your while. That's what I think, at least. I don't get why you got x equal to d. So let's look at the problem again. It says a block of mass m is pressed to height h above a spring with force constant capital K. We want to find the maximum distance d the spring is compressed. So d is defined as the compression distance of the spring. Haiti, does that make sense?
Oh, okay. So it's not like this. Okay, because I see that you put d as y also, so I got confused.
Well, I mean, d is also a distance, right? It's not just the compression distance of the spring. In this case, the object moves from this elevation to this elevation, right? So that's h plus d. So it can show up in both, basically. All right. Now let's go in here and let's write out what is 0. We said initial velocity and final velocity are 0. We didn't need to write either of these things down. These are both 0. We also said that the initial position, or initial compression of the spring was 0. And we said that we made y final to be equal to 0. So our entire equation has now reduced down to just 0 equals 1/2 k times x final squared. So minus comes outside, minus mg times y initial. We can now plug in our numbers. So we have 0 equals 1/2 k. X final was d, so this just becomes d squared, minus mg times y initial, which was d plus h. Something that's interesting to do, if you want to, you could go in and you could pick different values for y equal to 0, like you could make this point 0, or you could make the middle point 0, and you'd find that you always get the exact same equation, no matter what you choose, because regardless of what you pick for your 0 point, the change in y will always be the same. It doesn't matter. Okay, so that's the equation we have. Now, if you look at this equation, I know that we weren't given any variables in our problem, And this is where I kind of would like to actually plug numbers in at this point, and maybe we'll do that. What kind of equation is this? What are we solving for in this problem? It's a quadratic, right? Because we're solving for d. So this is a quadratic equation. I'm going to rewrite it like this. So each of these terms has an mg in it, right? Seems easier to just write it like that. And then we can plug that into a quadratic. So this is where, I don't know, like, I don't know if you all would find it useful to actually solve this with symbols. If we solve it with symbols, it's going to look something like this. I don't think that's particularly helpful. Does anyone think that's helpful? I don't. So let's just not do that. That's just kind of silly. We can't simplify it. It's whatever. So let's pick some numbers. So let's let big H be equal to, let's say, 5 meters. Let's let our spring constant be... this may give us answers that don't make any sense, by the way, but I think it should work. Let's let our spring constant be like 100 newtons per meter. And we'll let the mass be like 5 kilograms. And I don't know if this will help, but let's make g equal to 10. I don't know if that'll make the calculation simpler, but if we do that, then our equation will become k is 100. Mass we said was 5. And g we're using 10. Maximum is the vertex? What? What about maximum? I don't understand the question, I'm sorry. What maximum and what vertex? Oh, you're talking about the maximum distance here. It just means it's the place where the block comes to rest. It's the place where the spring basically starts to push back on the block and push it upwards. If that's what you mean by vertex, then maybe so. All right, k over 2mg. This is great because this coefficient's 1 now. That's awesome. All right, and then minus d, and then minus h, which is 5. So basically what is that 100 divided by 10 times 10? Yeah, that's 1. So we end up getting d squared minus d minus 5. It's too bad that... so if we picked 6 meters for h, let's do it. You guys, do you all care if I change this to 6? We haven't even used it yet. Let's just pick 6. Let's make it 6 meters. Stop it. This will be a 6. That looks awful. This will be a 6. And then we can do d minus... Wait. Well, I don't think I need to change k to 120, though, do I? That's why I wanted to make it 6. Why was the 5 easier? I think 6 easier.
I believe it's minus 3 plus 2.
Yeah, the first one I did was right. Wait. The coefficient doesn't have an h in it, though. Right? I don't know what you're all talking about. Yeah, it's okay. It's just because I had 5 and 5. That's probably why you all got confused. Yep. You're absolutely right, though. This is d. The first thing I wrote was correct. So it's d minus 3 and d plus 2. So we basically get that d is equal to 3 meters or d is equal to negative 2 meters. Those are the options, and of course this is going to be the right answer. And that's a pretty decent conservation of energy problem. What we'll do next time is we're going to do a couple more problems, and we're going to talk about power. So it's on the other notebook. Let me show you the you all can find this if you want to from the example packet, but the next problem we're going to do these two problems here. I'll just leave them as kind of the end of the stream or whatever. In fact, here, let's put them on the other slide because that's where they're going to go for the notes. So the next two problems that we will do will be these two right here. So if you want to think about them between now and then, you can. And I'll just say, are there any questions about the problem we just did? So this would mean the maximum distance would be 3 meters. The negative 2 would represent something about maybe, well, we don't have to worry too much about it. It doesn't really mean anything. Okay, if there's no questions, I'm just going to stop the stream for now, and I will see you all next time.